Hello, this is a tutorial on Principal Component Analysis, PCA, and the similarities and differences with Linear Discriminant Analysis, LDA. So let's dive in. The problem that we are looking at solving today is known as the curse of dimensionality. So this is the problem caused by the exponential increase in the number of samples or data points that is associated with adding extra dimensions to a mathematical space. So the basic idea over here is that performing pattern recognition in a high-dimensional space reduces the effectiveness and the efficiency of the pattern recognition system because of this problem of curse of dimensionality. What we are trying to do over here is to employ PCA or LDA as a dimensionality reduction method, or specifically feature projection technique that we use to reduce the dimensionality of the overall data that we are dealing with. Before I dive into the details of PCA and LDA, I need to remind you some basic concepts. So first of all, PCA is a multivariate technique. By multivariate, I mean that the method is capable of handling multiple features or multiple variables or multiple dimensions within your data set. The idea over here is that there are a number of these variables that are related with each other, or let's say correlated to each other, have some sort of similar information. We try to use PCA to transform the original features into a new domain where the resulting features are uncorrelated after projection. So PCA is a projection technique. You supply it with your original variables or features that you have formed somehow, and then PCA will give you a new set with the same number of samples, but with a different number of features. And these are the uncorrelated features. How PCA works? PCA is based on the idea of variance and covariance and correlation. So to understand everything related to PCA, let's first of all imagine this simple example where we have these data points over here, and we are looking at variance, as I said, as a measure of information. So within PCA, variance is one of the most important concepts. And over here, what we are trying to say is in which direction does your data points, or do your data points vary the most? So in this case, in the following example, this is the direction of the maximum variance. Why is this the direction? Because as you can see, if I put the center over here, the distances between these points at their center is the largest one. Perpendicular to this direction, which also gives you the first principal component, perpendicular to that is the second principal component, which is the next largest variance direction, in simple words, and like a very intuitive and simple word. So what we are trying to do over here is that come out with these principal components. Give me these vectors or projections that will describe most of the variance. Why do I need that? Because at the end, we might find that if we only know this principal component, if we only have that, we may have, let's say, like 90% of the information available or contained within your original data. So you might end up like throwing the other component. And by that, you do dimensionality reduction, as an example. To understand PCA, let's remember the difference between variance, covariance, and how correlation is related to these terms. So variance is a measure of spread of the data, as simple as it sounds. All what you have to think about, given a set of data points, these small yellow circles that I'm showing over here, variance is about computing the distance between each of these points, as you can see, and the average, global average, or let's say simply the mean. So what we are trying to do is take x sub I, which is each one of these points, and subtract that from the average, x bar. So I just made that slightly bigger, but just for intuitive reasons only. So variance is, as I said, the summation of these distances divided by n minus 1. And we usually denote that as s squared. When you have more than one variable, like x and y, the measure becomes a covariance rather than variance only. So variance is applied within one dimension. Between two dimensions, you need covariance. And this covariance measure tells us how much the two different variables vary from the mean with respect to each other. So that's the difference between x of I minus x bar, their mean, so the points and their representative mean, multiplied by the difference between the other like variable samples and their own mean. So y sub I minus y bar. In the case where x and y are completely replica of each other, the covariance turns into what? The variance, because this will be x sub I minus x bar times x sub I will be at minus x bar, so that will be squared, and that's the definition of the variance. Moving forward, we now know that there is a measure called variance, and between two variables, it becomes covariance. There is another measure that I need to bring to your attention, which is called the correlation, which is very related to variance and covariance. The correlation is given by the percentage of covariance between x and y divided by the standard deviation of x times standard deviation of y. So the correlation between the first and the second variable is usually S12 divided by S sub 1 and S sub 2. So in this case, I'm assuming that the covariance matrix, the capital S, is made of these components. So the diagonal is what? The variance of the individual component, the first and the second. And the off diagonal are what? The covariance values, if you remember it. So what we are saying is that the correlation is made by the division of S1, 2, by the square root of this factor and the square root of this factor. So from this, what you understand is that standard deviation of x is what? Is equivalent to the square root of the variance for each of the variables. So right here, as you can see, the idea over here is that if I want to make correlation 0, I need to kill the off-diagonal values, or take them or eliminate any kind of off-diagonal relationship by making them 0. So if I want to remove correlation, and this is how PCA does it, is that PCA generates a set of uncorrelated features by looking at the covariance and the correlation. And it says, I know that this is the definition of the correlation. I can't take these two components or the square root of the variance, so you can't touch the diagonal. Why? Because if you make them 0, either one of them, division by 0 will give you infinity. So what we do, we look at the off-diagonal value, which is S1 sub 2 in this case, because we only have two variables, and we try to eliminate these and make them 0. And that's the idea of PCA, eliminating the off-diagonal value. Now, if I go back over here, how do I eliminate the off-diagonal values? Well, there's one simple way to do that, which is, let's say we generate first the covariance matrix, which is, let's say, S, and then pre-multiply this covariance matrix S and post-multiply by a particular orthonormal matrix U. So it becomes U transpose times S times U. The diagonal values of the resultant matrix L are called the characteristic roots or eigenvalues of S, while the columns of U are called the eigenvectors of S. So we usually start now talking about eigenvalues and eigenvectors. And eigenvalues are directly related to the concept of variance. So the higher the value of the eigenvalue, it means the higher the amount of information or variance available in that specific vector, the eigenvector, corresponding eigenvector. So PCA and dimensionality reduction. How do I use PCA to perform a dimensionality reduction? So PCA allows us to compute linear transformation that maps the original data from the high dimensional space to a lower dimensional subspace by following two simple steps. The first includes transforming the original data with many variables into a new representation by looking at the eigenvectors, and like as I showed you in the previous slide, and then selecting only the first k projected variables for classification and ignoring the rest. Let me explain. Assume that you have a data matrix or data matrix, depending on where you're looking at this from. So assume that you have this data matrix, the number of samples over here, let's say they are n, and the number of features that you are looking at or considering are p. The first step that we do to implement PCA is compute the total average, and we call that x bar. Remove x bar or subtract x bar from x, which is the total data matrix. Look at the, like forming a covariance matrix, which is S, as we defined earlier, by multiplying x transpose times x. So originally x was n times p. We are looking at x transpose, so it's p times n, multiplied by n times p. You end up with a matrix that is actually p times p. In the fourth step, we calculate the eigenvalues and the eigenvectors of the resultant matrix, S, and then we use only the first few k vectors. So I only use few of the resulting eigenvectors. I don't use all of them. How do I know how many? That depends on your problem and the total percentage of variance that you are looking to keep. So at the end, remember that I started from somewhere where I had a matrix like that had n times p, so n samples times p features. I multiply that by the eigenvectors. So in this case will be p times k, and I end up with n times k. So let me remove these from there and put you the new matrix. The new matrix will also have n samples. We don't play with the samples, but we have actually reduced the dimensionality, the p. We have moved from p into k, and k over here is the number of the resulting components, which is usually smaller than p. The interpretation over here is that PCA projects the data along the direction of the maximum variance, as determined by the eigenvectors of the covariance matrix. As expected, the magnitudes of the eigenvalues correspond to the variance. So most of the, let's say, implementations will give you the eigenvectors and eigenvalues if you just provide the input like covariance matrix, and you look at the eigenvalues to determine how many of these like will you keep, how many dimensions are you going to keep by looking at the cumulative value of the eigenvalues. So usually we keep the first few principal components, and this is something that is really problem dependent. It's up to you to decide how many of these to keep and how many to throw away. Advantages of PCA include that in situations where your information is dispersed along or across the dimensions, PCA will consolidate that in an effective manner and allow you to use a few principal components to represent the whole set of information over there. Features produced by PCA are also mutually uncorrelated, so it minimizes the information redundancy, which is good for any classification problem. So PCA looks like it's doing a good job, but is PCA really a good criteria for classification? Maybe not, or maybe yes. Let's see. The main disadvantage with PCA is that PCA ignores the classification label when performing its analysis. So right now, we only looked at variance, covariance, and correlation. I've never mentioned anything related to the class label. So why do we assume that PCA will do good for classification problems? Like, I can understand that it's looking at maintaining information or the total information, but is that really good enough for classification? It will depend on the problem. Additionally, when projecting the data to achieve dimensionality reduction, we only keep a certain number of principal components. And as I said, you need to determine how many of these components you need to maintain or retain. So how to choose the number of retained components is usually hard to determine. in the old days, or was hard to determine in the old days. Nowadays, there are several methods that help you to look over there as well. Basically, it's problem dependent. Now, there's another method that is called LDA. Now, the funny thing over here, most of the new starters, or let's say people who just started looking at their degrees like master or PhD, they only know that LDA is a classifier, like linear discriminant analysis is a classifier. When you tell them that LDA is also available as a dimensionality reduction method, they are surprised. But LDA is used also as a feature projection technique or dimensionality reduction method, just like PCA. So how is that different from PCA? So far, I've been only looking at what? Variance and covariance. And again, I'm iterating on this because I'm trying to tell you that PCA have been looking at the distances with the what? The global mean or the global average. That's how we form the variance or covariance matrices. So by looking at the distance between each of the samples or each of the points and the global average, I made some sort of analysis. So is looking at the global average something good? So does that help me for classification? Let's have a look. In linear discriminant analysis, instead of projecting the data across the dimension of maximum variance, LDA attempt to project the data in a manner that will maximize the between class distances and minimize the within class distances. So what am I talking about? So looking at these points, previously with PCA, what I would do, I will just put the global average over here, and I will just calculate the distances between the points and the global average, which is here. Right now, we are saying we really care about classification label. So we need to account for that somehow. How do we account for that? Then we have to divide the data. We divide the data or the samples into two components. Within class scatter matrix, SW, so W means within, and between class scatter matrix, which is SB, so B means between. If I simply add the class labels, you will see now I have two sets of data points or samples. These are colored differently according to the different classes in the problem. So I'm assuming a binary classification problem over here. You can assume more than two classes. To form the between class scatter matrix, so what I really usually do over here is that, as the name implies, it says between class. So what I really need to do is look at the average of these, each one of these classes, and try to maximize the difference between these averages and the global average. Or alternatively, you can form the between class scatter matrix, by simply keeping these centers or averages of the different classes away from each other. So think about this simply. Instead of like looking at the global average that we were trying to get away from it for each of these different colors, now what I'm trying to do usually is that let's push these two set of points away in the opposite directions. Why? Because I need to maximize the difference between the samples that belong to the different classes. So purple and orange, push them away, each one of them, maximize the distance between these, then you will have good criteria for classification. This is one part of the objective function of linear discriminant analysis. So between class, remember this, push them away from each other to increase the distance between them. So you can guarantee, or you aim to guarantee, separation between these two classes. The other component, which is the within class scatter matrix, again, the same set of points. Previously, I was looking at separating the points from each other, like the two set of colors from each other. Now I'm looking at within class. So within each of the colors, look at the distances between each of the samples and the corresponding average, and try to minimize that. So remember, previously we were pushing the two colors away from each other, and now within each of the colors, I'm trying to bring the points closer to their average. And if you look at the matrix over here, what I'm doing, For each of the classes, I'm calculating what the distances between the samples and their corresponding average. So between the samples and the big orange, and between the purple samples and the big purple circle over here. Does this remind you of something again? Do you remember the covariance metrics? So does this relate to PCA somehow? Now, PCA was looking across all the samples and the global average, and that's called the total scatter matrix in PCA. In LDA, you are looking at the between classes scatter matrix and the within classes scatter matrix. So they are also covariance matrices, but at a smaller scale or at different scales. So our objective function or discrimination criteria in mathematical formula is usually what? The division of scatter between. You try to increase the distance between the different colors and minimize the distance between the samples with the same colors. So scatter between divided by scatter within. Or you can just simply take the inverse of SW times SB. So if you look at these two data points or the two graphs, these data points are exactly the same. So look over here, the red one's over here. So this is 1, 2, 3, 4. It's exactly located, or like exact replica of these points over here. So it's 1, 2, 3, 4, and there are 3 of them down there, and 3 of them down here as well. And similarly for the blue points. If you look at the direction that PCA looks at, which is the direction of maximal variance, this is the direction of maximal variance. There's no separation between the two classes. In fact, PCA may actually confuse the samples of the two classes. Why? Because PCA never considered the separation between the colors. It only looked at the direction of the maximum information variability. While with PCA, we look at the projection, which is this line, that will allow me to separate the two colors to the best possible way. So this is the main difference between PCA and LDA. LDA advantages include that it's a supervised feature projection technique or dimensionality reduction. By the way, I keep saying feature projection or dimensionality reduction. You need to know that dimensionality reduction can be performed either by feature projection, which include methods like PCA and LDA and others, or it can be implemented by feature selection. So feature projection is one method to perform dimensionality reduction. So the good thing about LDA is that it considers the class label, and as you saw in the previous example, that will give me really good projections that will give me the best classification outcomes. Additionally, unlike PCA, where I need to work out what is the best number of the projected features, LDA will always give me C-1 features, with C is the total number of classes in your problem. And this is determined by the rank of the scatter matrices. So why don't we just use LDA and ignore PCA completely? The thing over here that you need to know about LDA requires the scatter matrices to be non-singular. While for many real-world problems, scatter matrix may be singular. In the old days, around 2006, I used to work a lot on MATLAB, and at the days, I don't really know the differences here. At the time, I used to use the LDA classifier in MATLAB, and many of the times, I would just get the error that for the LDA classifier at the time, that the scatter matrices were non-singular. Or singular, sorry. So what's going on? At the time, I found that by removing correlated features, I can actually resolve that problem. There are like many other techniques to resolve the issue. But one problem over here is that the LDA requires the scatter matrices to be non-singular. And there are many reasons why they can become singular. So how would you resolve that issue with LDA? The second problem is that the number of features generated by LDA is always, as I said, bounded by C-1. So you always get C-1 features. But is that good enough for the different problems? Well, there are some problems that I've seen before that requires more features, or that require more features, sorry. Another limitation is imposed by the nature of the data itself. So, for example, many biosignals, especially used, like, for example, when you talk about using biosignals for sleep stage classification, when you look at the very deep stages of sleep, the patterns might be actually similar. So they are not really crisp. You can't say this pattern 100% belongs to class N1 or N2. You have to some sort of give membership or make it like fuzzy memberships. So the pattern become fuzzy in their nature. The pattern can belong to more than one class by some sort of, let's say, degree of membership. So how would you resolve that with this way of, let's say, crisp class association? Avoiding singularity. As I said, if the features are correlated, LDA will give you an issue because of that non-singularity requirement. So what people have been doing in the old days is that they have been adding PCA first and then implementing LDA. Alternatively, in the old days, there were also attempts to use SVD, singular value decomposition first, and then apply LDA. Why? Because the application of PCA or SVD, they are both techniques to generate the uncorrelated features, and then you can apply LDA. But instead of doing that, you can also use a regularization method, which changes the scatter within matrix by adding a small value to an identity matrix. So I have an identity matrix like this. I add a small value to the diagonal of it, and then add it to the scatter within. And that will resolve my issue. And the resultant method over here is called regularized linear discriminant analysis, RLDA. So in the old days, we had several options. I can apply PCA, then LDA, or SVD, then LDA, or I can just add a regularization and use RLDA. Nowadays, to heavily utilize variance, especially in the field of my electric control, which I mainly work on or still publish on a lot, the main two variants of LDA that are nowadays used include the uncorrelated linear discriminant analysis, ULDA. So instead of applying PCA and then LDA, some researchers came out with a method, said, hey, non, I don't really need to apply two of them to achieve uncorrelated features. I can change the way that I'm performing the eigenvector decomposition and take that away and apply a singular value decomposition and generate uncorrelated features while guaranteeing the linear discriminant analysis, like the approach is still there. So what we end up doing is that we are actually having an LDA method, but the resultant features are also uncorrelated. Another different implementation, which I tend to use myself heavily, is called the spectral regression discriminant analysis. With the spectral regression discriminant analysis, it also implements LDA, but instead of relying on SVD, which is computationally very heavy, unlike ULDA, they casted the problem like the researchers who developed SR or SRDA method. They casted the problem of LDA into a regression framework, which facilitates both efficient computation and the use of regularization techniques. So if you look into the recent papers using either one of these, remember, they both implement LDA. ULDA implements it through an SVD decomposition to generate some sort of uncorrelated features. SR casts the problem or the implementation of LDA as a regression framework, and it utilizes regularization techniques, which is really efficient and easy to use. So they both LDA, but implemented in different ways. PCA versus LDA. So although you might think that LDA should always be used, because based on the fact that it's using the classification label, it will always outperform PCA. But in reality, if you look into the literature, you will find many papers claiming that PCA outperformed LDA in their own experiments. PCA might outperform LDA when the number of samples per class is small, or when the training data non-uniformly sample the underlying distribution. So it depends on the data or the problem, the nature of the problem you are working on as well. A common factor between the two, PCA and LDA, they both rely on preserving the global Euclidean structure. So remember, they were actually both utilizing some sort of scatter matrices or covariance matrices, let's say. PCA was aiming at, let's say, or looking at the distances between the samples and the global average, while LDA was actually looking through the two scatter matrices, scatter between and scatter within, at, let's say, the average of the between the average of the different classes, and like increasing the separation between the averages of these different classes, and was also looking at the scatter between, which we were looking at minimizing the distance between the samples and the corresponding class average. So what we are doing over there with PCA and LDA, we are always looking at some sort of global representative of these points. It's either the global average of all the data or the average of the corresponding classes. Differently from that, there are nowadays so many other methods, including but not limited to TSNE, neighborhood preserving embedding, locality preserving projection, locality sensitive discriminant analysis, and others. They are focused on preserving the local manifold structure, which means instead of looking at the distances between the samples and the averages, they actually, or this new set of methods on the right, they are actually looking at maintaining the distances between each samples and its k nearest neighbors. And that's how they form their manifold structures or graph Laplacian matrices. So they start by forming some sort of distance matrix between each samples and its remaining k nearest neighbors. And the idea is that if you maintain the distance between each of the points and its k nearest neighbors, then you guarantee that in the projection or the projected space, you will have some sort of meaningful, let's say, projections. So for certain problems, adopting methods that focus on preserving the local manifold structure might be more important than the global structure for discriminant analysis or even PCA. So new variations of PCA and LDA are nowadays available, but I just wanted to bring the basic concept of PCA and LDA. So new variations of PCA also takes the class label into consideration. These were recently proposed. Examples over here from the literature, very famous ones about the application of PCA and LDA. Whenever you hear about eigenfaces, remember that these were generated by applying PCA only. And you can see that they are really representative of the underlying faces. Feature faces are the result of applying LDA feature projection. So Fisher is the guy who invented these linear discriminant analysis techniques. So just want to give you an examples. Thank you very much, and I hope you have learned something today.